coming up on StarTalk, Cosmic Queries. I've got Chuck Nice with me, and we have as our guest, theoretical physicist Delilah Gates, and she's an expert on everything space-time geometry. We're going to learn what that is. We're going to find out if in a spherical universe, whether we can see the back of the head of our own Milky Way, does the rest of the universe abide by Newton's laws or Einstein's laws? Is the universe curved? And is there a center of the universe? All of this lives within the understandings of the universe that comes to us by studying the space-time continuum of it. Next on StarTalk. This is StarTalk, Cosmic Queries Edition. I got Chuck Nice with me to help me out here. Chuck, how you doing, man?
Hey, Neil, what's happening?
All right. This is a Cosmic Queries on gravity and space-time geometry.
Oh, my. I think, why aren't we being a little, we really should be as elementary as possible,
Just basic, get the basics out there.
We need to get these basics out of the way. And I think this is a great time to do it,
Yeah. So whatever I know about this, it's not enough to do a whole show on it. And
Okay.
So we found one of the world's experts on this subject. And
Right.
she's with us today, Delilah Gates. Delilah, welcome to StarTalk.
Hi, thanks for having me.
Hey.
Yeah. And from your resume here, you were freshly minted PhD, like 18 months ago or something. Am I getting that right?
That's absolutely
man.
right.
Oh, wow. You know what?
Spanking brand new.
I thought that was it. You got that new Dr. Smell. I thought.
Well, as long as it's a pleasant one, I'll take it.
There you go.
Absolutely. Wouldn't have
So
any other way.
you got your PhD in physics from Harvard a couple of years ago, and now you're at the Princeton Gravity Initiative. So,
That's right.
what is that? What does that even mean?
So, yeah, the Gravity Initiative is a center here at Princeton. And most of the people involved with it are postdocs and affiliated professors and a few grad students. And we are a bunch of people who ask questions about compact objects, by which I mean objects that have the strongest gravity that we have in our universe. That's black holes and neutron stars. And also people who study questions of math related to general relativity and gravity as well.
So,
Wow.
is that because what Einstein realized was that there are entire branches of mathematics that you need that the physicist might not have expertise in, and then the mathematicians come in to help out? Is that kind of what happens there?
That's kind of what happens. It's actually an interesting back and forth. So, of course, discovering Einstein's equations and the solutions to it that describe the shape of space-time around things like black holes was revolutionary. And of course, new math needed to be introduced to be able to calculate these objects. But additionally, just the fact that we now know our universe hosts these objects, black holes, neutron stars, these strong gravity environments, leads to just mathematical questions about whether space-time itself is stable, for instance. And so the mathematicians have a back and forth interplay with the physicists when it comes to asking questions about gravity.
Delilah, that completely spooked me when you
I
said
said stable.
space-time might not be stable.
Exactly. It's like, what happened? Did we break up with another universe in the multi-universe?
The question of stability is shouldn't be as scary as it sounds. Certainly, we think it should be stable. It hasn't broken yet. We're still all here to ask these questions, so we don't think it's broken yet. It's more so just though mathematically understanding if something is stable is a little bit different from, just by fiat saying we exist, therefore it is. So
And Chuck, it has nothing to do with emotional stability.
Well,
just to be clear, okay?
That's where I'm going to go immediately.
Right.
Yes.
So Delilah, tell us what space-time is and space-time geometry, just so we're all on the same page.
Absolutely. So let me back up a little bit and just talk about, our own intuition. We live in a world where we're able to move around and we kind of can get this feel that there are three dimensions in which we can move. We can move back and forth, we can move left to right, or we can move up and down, right? And so that feels like three dimensions. And, for a long time we used classical mechanics and Newtonian gravity to describe what was going on in that situation. But when Einstein came along with special relativity, he told us that time, the way we perceive sequences of events, is also related to the dimensions that feel like spatial dimensions to us. So what we actually have to do is think of space and time as being one object. And to move from thinking about them as just one object, this object also has a shape. And this is when Einstein added general relativity to tell us about what that shape is. There's this relationship between the shape of quote unquote space-time, this fabric that we all live in, which has to do with the way we're allowed to move physically through space, as well as the way we perceive time flowing in space. This one object is shaped by the stuff that's in it. So gravity, as given to us by general relativity from Einstein, tells us energy and matter tell space-time how to be shaped, and the way that space-time is shaped tells matter how to move throughout space-time, what paths it should take.
Wow. Well
All right,
done.
and so when you have your high gravity objects, that tests your ideas and the mathematics at their limits in a way, right? Because I guess everything that you described is happening here and now around us, but it's not manifesting in any important way that we would change our lives based on it, right?
That's right. It's true that for the most part, we can use, classical mechanics and Newtonian gravity for the way things are, and we don't have to appeal to
Delilah, it was good enough. It was good enough for my grandparents. Okay.
Hey, it's honestly good enough for all of us when we drive our cars, when we throw baseballs. We don't have to think about, oh my goodness, how is the baseball warping space and time as I throw it to my friend?
Yeah, in my generation, that was good enough for us.
I think most of us actually live our physical, intuitive lives without having to appeal to it. But even in the time of Einstein, it became relevant. It was, first tested, general relativity and the corrections it makes to Newtonian's gravity was first tested using solar eclipses. So even the way our sky appears, is affected by general relativity, even though we don't need it for the way we intuitively move about our day for the most part.
Plus, as I understand it, the entire Apollo program used just Newtonian gravity. So, look, it was good enough for us to get to the moon.
Absolutely.
You young whippersnappers that are trying to do something extra with it. So we have questions that we solicited from our Patreon fan base. And if you want to ask questions too out there, you can join our Patreon. And there's a pretty affordable lowest level where you get to ask these questions. And so, Chuck, you compiled them?
Yeah, these are all specifically for Delilah. Christine Dolman says, hello, Dr. Tyson, Dr. Gates, and Sir Chuck. No, that's Lord Chuck, Christine. I'm a teacher and a young scientist. I love facilitating the study of geometry. How are 2- and 3-dimensional shapes represented across the universe? Spheres are easy, but what about the rest? Aha, yes. Well, the spheres happen even here, naturally. Underwater, and for some reason, everything becomes a sphere. So what's going on there? And what about the rest?
Well, I guess, when thinking about the shapes of various things, often the question is, what is energetically easy? Spheres are easy, and it's because, you can make things smooth and try to, fit a minimal surface area around a maximal amount of volume. If you think about, a fun thing is if you think about water in space, if you have a drop of water, it's roughly spherical when it floats in space, unencumbered by the force of gravity. Of course, if you touch it a little bit, it'll vibrate and wiggle, but it wants to be spherical because of the surface tension, trying to find an easy way to relax. But I will say, what about the rest, about shapes throughout space? If we're thinking about objects, one thing that I think is profound is that in physics, we kind of think that things are generic. We think that the laws of physics here are the laws of physics everywhere. And we try to come up with theories that describe the whole of what happens anywhere in the universe. And of course, this is what we want. I do hope the way I throw a ball is the same way I would throw it on one side of the Earth or another side of the Earth, or if I went to the moon, as long as I calculate for the change in the mass of the planet I'm standing on. So the shapes should all be described in the same way, regardless of where we are in the universe.
Okay.
Oh, that's okay. That's very clean.
That's very clean.
Yeah, all right.
Okay.
On Earth as it is in the heavens. Yes.
That was good. All right.
All right,
Well, that was
Chuck,
great.
give me another one.
Great
Yeah.
question, Christine Tolman. Thanks. This is Trevor C. Mills. Trevor is coming to us from Augusta, Georgia. He says, greetings, Dr. Tyson, Dr. Gates, and Chuck. I know that currently it is not believed that wormholes, sizable ones at least, have the ability to be stable. Is this due to the geometry of space-time itself? If so, what about the geometry of space-time prevents stable wormholes? And if not, then what does prevent stable wormholes?
So this is,
When people ask that, I try to ask them how old they are, because if they're like 12 or 13, then you got to check the basement, see if they're making something down there. This is how you get the nemesis of superheroes. Sounds like an innocent question, on the surface.
Yes, yeah.
So Delilah,
an addendum here is, and if I were to create a wormhole, would I be able to get $1 billion? Okay.
hey, I'm sure if we created a wormhole, someone would try to use it to make money.
Yeah.
For nefarious ways. So Delilah, we mentioned instabilities earlier, and here we're talking about the stability of a wormhole. So what's up with that?
So I will say, as a caveat, my expertise is not math. So this is a question, the mathematical side as a mathematician of general relativity or space-time geometries. But from my understanding, this goes to the question of the way things change when you add additional matter. Often when we solve for the shape of space-time in Einstein's equations analytically, we only do it in specific circumstances where all the matter is only, say, in the black hole or the neutron star, very compact. But of course, if you want to jump through a wormhole, you're yourself matter. And if you are matter, you cause, according to Einstein's equations, the shape of space-time to change slightly. So when mathematicians try to understand the stability of space-time, of certain space-time objects like black holes or wormholes, what they really have to do is add a little bit to the mathematical description of the shape to account for adding, say, a person trying to jump through the wormhole. And then you have to calculate whether or not the equations break down or can settle back down into their original form once the person has moved through the wormhole. And that's a hard thing to do. I don't know what the generic rules are about what make this up, but typically stability is not an easy thing to prove. It's still an open question whether spinning black holes are stable.
I'd heard we need some kind of negative gravity to do this. Is that correct? To pry it open? I had some vague memory of this.
This is not something I'm familiar about, whether negative gravity is necessary.
Wow.
Okay.
Sorry.
How does negative gravity work? It's like I tried to be on Earth, but it kept throwing me off.
Well, in a way, we could consider dark energy negative gravity,
Oh, yeah.
Well, that's what I'm
Gravity
saying.
is the
That's what
idea
I'm
that
saying.
things want to clump
Come
together.
together. So, yeah.
Exactly. But the universe, because of dark energy, wants to spread apart.
Okay.
Right apart. Right.
So, wow.
Right.
Negative gravity is dark energy. That's pretty cool, man.
Yeah, it's
At
like
least in a
sort of
sense.
negative
In a sense,
energy
right.
density. Yeah.
Cool.
Oh, okay.
All right.
All right. So what you're saying is it's still not a completely solved problem, which is interesting, which keeps open the doorway for science fiction writers. And I don't have a problem with that. As long as we give them a little bit of latitude, let them run with it.
It also keeps the door open for mathematicians who want to study the area.
All right. What do you have next?
All right, here we go. This is, let's see here. Let's move away from home and go to Quentin in Switzerland. And Quentin says, if the universe has a closed spherical shape, could one of the galaxies in the sky that we look at be the Milky Way in its past state? Oh, wow. So can we look out and then see around?
Come around the backside.
We come around the backside
Hey,
looking
Chuck,
out
is
the
that, is
front.
that the back of your head, Chuck?
Yeah, exactly. How did that happen, man?
Chuck,
I'm
move
looking,
out of
looking
the
at
way,
these
Chuck. I'm trying to
binoculars and I see I need to get a shape up in the back of my head.
Actually, we got to take a quick break, but when we come back, we're going to find out the answer to whether, if the universe is spherical, does looking out in one direction end up coming right back so that you can see the back of your own head, or at least the back of the Milky Way's head, when StarTalk continues with our guest, Delilah Gates. We're back, StarTalk, Cosmic Queries, talking about space-time geometry and gravitation with freshly minted PhD, Delilah Gates, who is now at Princeton University in their Gravity Initiative program. That's just so audacious. It's like, no, there's still some gravity we don't understand, and we got to figure this out, and let's get some smart people all in the same place at the same time. See what I did there?
Yeah.
Look at that.
See how clever I was with that,
Those
right?
Space-time jokes.
I know. This is a question from Switzerland. You just read it back real quick, Chuck.
Sure thing. Sure thing. This is Quentin from Switzerland. He said, if the universe had a closed spherical shape, could one of the galaxies in the sky be the Milky Way in its past state? Interesting.
So this is a great question. And in principle, the answer is if the universe had a closed spherical geometry, then indeed we could see our own Milky Way in the sky. But there is one problem, however, or one other element you need to consider. Even if the universe is spherical, you also have to consider its size. There would have had to be enough time since the Milky Way started for the light from it to reach us. So even if the universe was spherical, but the universe was too big, the light from our universe that went around all the back around and then to come back at us wouldn't have had enough time. So in principle, the answer is yes, but you also need to consider how large the universe is.
Wow.
To understand whether or not one would be our own galaxy that we're seeing in our sky.
Then what's the answer for this universe? Then we should know that, right?
Well,
are we big enough, or are we small enough for that?
Yeah, we don't see any evidence that that the observable universe, in all the light we can see from starting close to the Big Bang with things like the cosmic microwave background, we don't see any evidence that our universe is closed and spherical.
Okay.
Oh, wow.
Another thing is we
All
also, if you talk about whether the universe is closed, it doesn't have to be a sphere. There are other closed geometries, like tori. And
I don't know what a tori is.
Oh, a tori is a donut.
It's the plural of Taurus, dude.
A
It's
torus.
a plural of Taurus, dude.
Now
Taurus
I know.
It's not an astrology sign. It's a donut.
Gotcha. Okay. That's the first time I ever heard tori. Okay.
We just plural of Taurus. All right. So what you're saying is we're in an open universe, not a closed universe.
Not a closed.
We think
one.
there's definitely no evidence we're in a closed one, and there's also no evidence that we are on a geometry that is curved like a sphere. For instance, if you didn't knew the universe was big enough that you couldn't have seen the light from yourself wrapped back around, you might say that doesn't matter. I can just look at the overall curvature of the space-time, and we don't have any evidence that the curvature of the space-time isn't flat. Our evidence has an error constraining it around being flat geometry.
So in other words, the uncertainties even in our understanding of the flat universe do not include the possibility of us being closed.
Well, yes, that's correct. That's correct.
Wow.
Right.
So,
okay.
but intuitively, when you think about it, we know the universe is expanding, and you look into space, doesn't it have to be expanding in all directions all at once? Which the only thing that we know that goes in all directions all at once is, like a sphere, an ellipse, or something like that. So intuitively, your mind goes to, it's got to be shaped like that.
I think intuitively from geometry that we understand might suspect that, but actually I think that's a little bit of where you have to actually use your math to tell you that you should be careful of your own intuition, because at large scales we don't necessarily intuitively have to live by the rules of, say, Newtonian gravity.
Ah,
Just because consider, just a plane. If you were a two-dimensional being and you lived on a plane, that plane could go on forever without having to be wrapped around such that it didn't have such that it closed in on itself. So it could just be you're on an infinite plane. And then, of course, you can extend that into 3D to have an infinite volume.
right.
So
Okay.
intuitively, this is a case where we got to check our math and tell ourselves we don't necessarily have to be in a closed universe.
I love it.
Yeah, so
Look at
Chuck,
that.
stop using your damn intuition, okay? That's what.
Oh, believe me, that we gave up on that a long time ago.
I opened one of my books with the statement, "The universe is under no obligation to make sense to you."
Yeah, it's very cool.
Just put that
I
out
love
there.
that.
We like
Put it out
it.
there.
We like that. Okay.
What more do you have, Chuck?
Shall
Coming
we?
from our
Let's-
Patreon members.
Let's keep on going with Patreon member Dylan, who says, "Greetings, Dr. Tyson, Dr. Gates, Chucky baby. Undergrad astrophysics at NAU in Flagstaff, that's where you'll find me. General relativity allows for 3 possible shapes of the universe, Euclidean, positive, and negative curvatures. Curious on which shape you most lean towards." So we just got finished talking about, how we got to check the math, not to be relying on our intuition. But now we have a question directly to you, Doc. Well, where do you come down on the whole shape issue?
Well, I tend to be conservative and trust my colleagues, and so there's amazing experimentalists out there who have so far shown us that we shouldn't expect that the universe overall has a curvature. So I definitely lean towards it being flat. I will say, when people ask this question, I want to caveat this is on large scales. Of course, gravity tells us that there is curvature where there's matter.
Right,
So certainly
of course.
around black holes, the space-time is very curved, but it's like on large scales, if you average it, we think
Yeah.
it's relatively flat.
Yeah, and to your
Okay.
last point, we have pictures of that. That's, of course, we think that because we've actually seen it, not the black hole itself, but how light interplays around the black hole, so we know that what you just said, that it's curved. That's
Absolutely. Speaking of black holes, we had a question earlier about this idea of seeing the back of our Milky Way if we were in a closed spherical, small enough geometry for our universe. Even if we're not, a place where you can potentially see the back side of your own head is actually around a black hole. Black holes have a region around them called the photon sphere. And this is a region where light can wrap around many times around the black hole, coming pretty close to its original position before either spiraling out very far away from the black hole or falling into the black hole. So if you want to see the back of your
Damn.
head, go near a black hole.
Well, so the light is basically in orbit around the black hole, in a sense.
That's right.
Is that a
So
fair way
cool.
to say that? Yeah. So you look straight ahead, and you will see light that headed backwards and came around to the front of your face, and that would be the nappy back of your head.
That's
You
right.
gotta go to the
There we go.
barbershop.
That's what we're talking about.
Right.
Wow, that is
Right.
so cool.
That would make for a weird picnic, Do you know who you're looking at? Who do you
Right.
see the front and the back of them at the same time, and then you walk towards them, but you don't know which one you look. I mean,
Yeah.
that's something somebody needs to do in a movie.
Yeah.
Oh, absolutely. I imagine it'd be very disorienting.
Yeah. Worst
Yes,
movie
completely.
worst movie theater ever. Down in front. Oh wow. Oh, that's a fascinating,
check.
fascinating little
The
tidbit.
photon sphere, very cool.
The
Okay.
photon sphere. Love
So
it.
keep it
love
going,
love it.
Chuck.
All right, here we go. This is Tegan Messier. And Tegan says, "Hello, Dr. Gates. This is Tegan from British Columbia here. What shape do you think our universe is?" We already said that. I heard an idea that it could be shaped like the DNA molecule, since the DNA is the best way to store information that we are aware of. Any thoughts on this? So now the reason why I read this is because there are a lot of people who actually make connections between our own physiology, our brain, our neurosynaptical systems, and the universe itself. Do you see any connection there?
I will say there's The shape of DNA is a kind of funny and windy shape, so there's no reason to expect that to be the shape of our universe. But I do think there are a lot of beautiful analogies between humanity, our own DNA, the structures, shapes of things here on Earth, and the shape of things that we see in the sky, like the shape of where matter is following the galaxies and dark matter. If we run simulations to see where the stuff is clumped, it has interesting patterns that feel a lot of like kinds of natural, quote unquote, patterns we'd see here on Earth. And I think one of my favorite analogies between humanity and the universe is the fact that we're all made up of cells, and yet we are conscious. And so we're tiny cells that somehow have become conscious and can ask questions about ourselves. In the same way, we are made up of the same stuff as the rest of the universe. And so humanity and any other sentient life out there that's asking such questions is really, made up of these tiny things and then able to query itself about itself, where the universe asking itself about itself. And I think that's pretty darn cool.
Oh,
Damn.
Damn.
All right. Good night.
That's
Good
a
night,
variant.
ladies and gentlemen. That's our show.
You can't follow that with anything, right?
What do you do with that?
So I think it was in the Carl Sagan era, there was the phrase, humans are a way for the universe to know itself.
Ooh.
And I that sounds all poetic, but it's kind of egocentric because it implies that we are the ultimate source of how the universe can know itself, when it could have made some way smarter aliens around in the other sector. Okay.
Well, I did say us and any other sentient beings out there.
Yeah.
I do think it's humorous to think we're alone.
Good. Completely, of course. Yes.
Oh, look at that. We are
Chuck,
not
keep
alone.
it going.
Look at that. So all you extraterrestrial enthusiasts out there, we're not alone. You just heard it here. Okay. This is Brian Lacey. Hello, it's Brian from Baltimore. I've heard of toroidal shapes, like the donut, and that our universe may even be that. How does it work in, wait a minute, here's the questions, because we just touched on that. So just to let you know, I'm not crazy. How does this work in upper dimensions? So that's the difference from what we just touched upon about the tori. So, how do things change once we get to other dimensions?
So if we add dimensions, actually, depending on what we're describing, things don't change too much. We can think about, we know how to measure the curvature of shapes. Actually, it turns out intrinsically, which means we don't have to embed them in higher dimensions to know how to measure their curvature. So, you might think I can measure the shape of a circle because I can hold an object that's a circle. But if I lived on the circle, I wouldn't be able to describe its shape unless it was small enough for me to walk all the way around and come back to the same point. But in geometry, this isn't quite true. There are intrinsic ways in principle to measure curvature. So we can get at the curvature even if we live in the space-time. And so the same measures we would use to say, is space-time curved, in our 3 + 1, that means 3 space plus 1 time, space-time that we live in, we could play the same mathematical games and use similar experiments that we've developed to measure the shape of space-time in higher dimensions. It turns out.
So what does a higher dimensional torus look like? Like, what is that?
Well, it's a shape I can't draw on a piece of paper because we only have so many dimensions. But it's more or less in a way similar to what we have now. You could think of having describing a torus, at least topologically. You can describe a torus as taking a closed object like a sphere and then puncturing it, and you can count. You can describe tori by how many punctures they have. There's the donut, which has 1 puncture. You've seen inner tubes when you go down like a water slide where 2 people can sit on it. That's a torus with 2 holes, or we call the holes genus. And so you can do the same game in higher dimensions, and you can say, starting with a closed shape, and I puncture holes into it, and I can describe it by how many holes it has.
Whoa, that is really dope. That is cool. Awesome.
The next time I'm on a 2-seater water slide, I'll be thinking of this conversation.
Absolutely.
For sure. Right.
All
I think
right.
that's one of the fun things
Right.
about being a physicist is you can think about analogies to the stuff you're learning in physics and math, geometry, etc. When you come across everyday objects, and it makes them, in my mind, feel even more exciting to think about.
Mm-hmm. Mm-hmm. Mm-hmm.
Cool.
All right.
All right.
Chuck, keep it going.
This is Hi Do, and Hi Do says, "Hello, Dr. Gates, Dr. Tyson, Lord Nice. I've always wondered if the golden ratio ever applied to anything astrophysical in nature. If not, why? We hear it used often with terrestrial architecture, art, music, etc. Do you ever find these examples in astrophysics?"
Wow. So maybe Neil can tell us more, but to my understanding, I'm not sure that the golden ratio tends to pop up in any astronomical observables or measures, to my knowledge.
I haven't seen it either. Yeah. So
Yeah. I think
yeah,
one thing that
kind of
does,
like
in a sense, pop up more often is pi, but that's because pi is related to spheres. So a lot of
all right.
equations, like Einstein's equation, for instance, has pi in it.
It is weird. Pi shows up in the most unlikely places that you'd ever think.
Yes.
And there it is. Like, how'd you get it? Who let you in?
Who ordered that?
Right,
Hey,
right.
Some of us
Exactly.
order pizza pies, and some of us order the number pie.
There you go. All right. Let's move on. This is Zuber Singh. He says, "Hello, Dr. Gates, Dr. Tyson, and Chuck. Here's my question. How does the geometry of space-time change in the presence of massive objects like a black hole? And how does this affect motion of objects in the vicinity of those massive objects?" So, I mean, if you want to talk truly massive, it have to be, black holes at the center of our galaxies.
Absolutely. So, we all know that our planets, for instance, in our solar system orbit the sun. And so this is this effect where we can get matter to travel around an object many times is namely one of the biggest features of having massive mass really concentrated. And so when we concentrate mass even more into a smaller area and we get even heavier objects, these effects get more and more pronounced. Namely, for black holes, the defining feature of them is that you have so much gravity that not only is it planets or other massive objects that can get on paths that are closed, you also can get the same thing happening to light. And you can even get it such that you have the event horizon gravity so strong that even light can escape from the black hole if it gets too close. So it's just a bigger and more pronounced effect of what you probably know from your astronomy classes or science class when you learn about planets being able to be on orbits. And if, like I mentioned, the photon sphere earlier, you can get light bending around black holes multiple times. And of course, you have the defining feature of them, the event horizon, the surface around the black hole, the area from which if light goes to that area, that it won't be able to escape the gravity and leave the black hole, excuse me.
That's pretty cool. Yeah, now you just said, with this photon sphere again, and what just popped into my head as a question is, how are you recognizing the same light as opposed to the new light that's coming in from behind the black hole? So how are you identifying these are the same photons that we just registered whenever?
Great question. So if you are thinking about the problem from a mathematical standpoint, you can do the following. You can say, I can shoot light from different positions around the black hole and watch and calculate all the paths that it can take. And so it's when you do that, if you say I have a source here and an observer here, I shoot off light and I watch the different paths that connect my observer and my source, or my source and my observer, then you can just look at the different paths to see how many times it winds. In actuality, in the real world, we don't have experiments that are so powerful yet that we can necessarily easily detect the light from an object being the light that wound many times. But in principle, one could look at, say, a black hole that has stuff spiraling around it, and they could look for statistically correlations in the image to know that they saw light from that object that wound different amounts of time.
Okay. All right. Excellent.
Chuck, we got to take a break.
Oh, okay.
When we come back, we'll come back for our third and final segment of Cosmic Queries, Spacetime Continuum Edition, when StarTalk returns. We're back, StarTalk, Cosmic Queries. We're talking about the space-time continuum with Dr. Delilah Gates of Princeton University. Do I understand correctly that you make an appearance in a Netflix series? What's it called here? A Trip to Infinity? Is that correct?
That's correct. There's a Netflix special called A Trip to Infinity, which I appear in, and it has experts, mathematicians, physicists, philosophers, and we take the chance to discuss what it's like to try to grapple with the concept of infinity, what it means to mathematicians and physicists and philosophers, and try to give people a way to understand it. I don't really care for self-promotion, but I think it's wonderfully done, has beautiful animations, and can give anyone the sense of awe that I feel and that I think many physicists and scientists feel who think about these kinds of problems when we do our work.
I love it. I have it bookmarked, and I haven't watched it, but now I'm going to watch it. All right,
Chuck, we have last segment.
Last segment. We'll make it quick. I mean, I'll keep things moving, but first, let me just give the PS to Zuber Singh, who I promised that I would, but and he says, my educational background is in the humanities, but because of Neil and Cosmos, I am now a huge fan of astrophysics. Love what you're doing.
Nice.
Just wanted to say that. Okay. Okay, let's do this. This is Colby Lepresi who says this. Hey, it's Colby from South Carolina here. Hi, Neil. Hi, Chuck. Hi, Dr. Gates. Why do we always see galaxies appear closer and closer together when we look deeper and deeper in space? Does this have any indication of the shape of the cosmos? I get that we're looking back, but what's the deal? Okay, there you go.
I think the deal is twofold. I think one, as we can see further and further away, of course, if you think about having a forest and you can only see the trees a certain distance, and then you can see you can add on distances, it seems more dense. Not that they weren't always there, but just because you have farther depth in your vision. So it seems more crowded because you're seeing further and further away galaxies stacked on top of each other. So that's one. And then two.
But that's a line of sight. So that's a line of sight thing.
That's a line of sight thing. And then I think the other.
It's not that they're actually next to each other. They're just lined up in your line of sight, and they feel like they're crowding.
Exactly. And I think
in photography, that's called depth of field. And when you use a longer lens to take a picture, you can squish things together with a telephoto lens. But go ahead.
Absolutely. So there's the depth of field, but then also because the way we view things kind of, from one position. If you view things in a cone, so you have a conical view outward. So additionally, you can stack more things kind of directly behind each other, so it looks denser, but you also, as you look out, you see a conical kind of field of view. And so you have, based on just the shape of a cone, right, you can fit less things here than you can fit at the top of the cone. And so the top of the cone, the things that are farther away, you can also see more of those. So I think part of it is depth, as well as the fact that we view things conically. So it looks like we're seeing more and more. And then, but it's not actually a statement necessarily about something having fundamentally changed. Those galaxies were there. They've been there for a long time. It's just we have new technology.
And by the way, galaxies do collide, so it's not that does happen. But I want to add something here, and that is in the past, because if you look out in space, you're looking back in time, the universe was smaller than it is today. So this angle of view that you send out to the edge of the universe actually encloses much more of the universe in the early time than it does in the later time, simply because the universe was smaller. It's an interesting phenomenon that we see. So we have to adjust measures of the distances between things that we get from the angle that we see. So it would be distortions on this cone that Delilah was talking about. Yeah.
Wow.
So the
okay.
cone doesn't go straight out. The cone actually focuses back a bit as you go out there. And so cramming in more of the universe into the field of view. It's a pretty cool effect, actually. Yeah.
Great
let's keep going.
question there, Colby.
Time for a couple
appreciate
more.
You. This
All
is
right.
Woody from Adelaide, who says, I often see
Adelaide, Australia.
Yes, sir.
Australia, okay.
And yeah, we're getting them from all over the world today, man.
Right, all right.
People are interested in this this subject. Woody says, I often see visualizations and descriptions of the fabric of space-time where a 3D structure stretches and bends. But is it possible for space-time to be anything like a fluid near or inside of an event horizon?
Oh, I like that.
Wow, look
fluid.
at that.
Ooh.
Fluid.
So I'll start with the fact that we don't know what happens inside of an event horizon. We can make mathematical speculations, but like Neil said, the universe is not obligated to be understandable by us or be in accordance with what we've so far calculated. And since an event horizon, by definition, is a region from which light cannot escape, we can get no information about what's behind it, at least as far as our understanding is today. But if we even think about the space-time that we have outside of black holes, we can think of it in a way as something that is in motion. Because sources of, that's things like black holes, galaxies, planets, all these things are moving. So the shape of space-time around them is also always dynamically changing and adjusting as the matter moves on top of it. And in fact, in order to understand the gravitational wave detections that we have from LIGO and the other experiments, Kagra and such, we have to dynamically calculate the way space-time changes, stretches and contracts because of the two massive objects spinning in on each other to emit gravitational waves. So in fact, yes, the universe is like a fabric or a geometrical shape, but it's not rigid.
Not rigid.
Not
there
rigid.
It is. Right.
Okay.
Right.
Look at that.
Okay.
Fascinating
Cool.
stuff. Fascinating stuff. Let's
All right.
keep
Another one,
moving
Chuck.
on. Okay, here we go. This is Bruce Ryan. Bruce Ryan is from Alexandria, Virginia. He says, I once heard Neil say that there is no center of the universe. Hey, what's up with that? If the universe started from a single point, there has to be a center at some moment. Okay.
All right, Delilah, dig us out of that one.
So this is the, again, where our intuition is fooling us if we think about what we're used to. But in fact, we know, for instance, that the universe is probably not shaped like a sphere, but for a moment, suppose it was. If it was shaped like a sphere, and you're a person who lives on this sphere, who's to say what point is more special than any other point on that sphere? And so when we say that the universe is expanding, it's not talking about us expanding away from any one given point that's the center. It's the whole thing expanding in size. Think of drawing a point on the surface of a balloon and then blowing up the balloon. All points on the surface of the sphere get farther and farther away from each other, but none of them is more special than the others. And this is what we mean when we say there's no center to the universe, despite the fact that it's expanding.
I like to think of it that there is a center, but you can only find it if you go back in time. It's a place in time, not in space.
Yes.
Ooh,
yes.
What do you think of that?
Excellent. A place in time.
Yeah.
See, my answer is
But
the
not in
center
space.
of the universe is, in the words of Little Richard, me.
Okay. Is Little Richard the only one who have ever said me? Is that you got to go to him? for that
He's
one.
the only
Okay.
one that ever said it like that.
Like that. That's right.
Like that, yes.
All
which
right.
I love. Okay. Sorry. Just wanted to give him a shout out. Love that guy. He's dead, but who cares? All right.
All right, quick
that-
last one. Give it to me.
Can we get a last
Last
one? in?
one.
All right. Let me find
Last
something
one.
here that is quick.
Delilah,
Okay,
you got to
here we
go on soundbite mode.
All right.
Delilah. Okay. All right. Let's go.
All right, this is Jesse Desmond. Okay, I picked the wrong one because I don't even know what this is, but I'm going to do it anyway. Could the Mandela Effect be the result of a parallel universe colliding with ours? Imagine two bubbles colliding, but instead of bursting, they form a double bubble.
I hesitate to say the answer. I hesitate to say yes to that. I just because I don't understand how mathematically we would set up the situation to describe this, and mathematics is king in theoretical physics. You have to write down your theory and then test it. So
Okay.
if we don't have that, I hesitate to put any weight behind it. Sorry.
So
And remind us of the Mandela Effect described here. Is that?
The Mandela Effect is this effect where we misremember, like large swaths of people will remember something falsely, like Luke, I am your father in Star Wars. I think he just says, I am your father. I think there's
he
no
never
Luke
says
before
Luke.
it. Or Berenstain Bears versus Berenstain Bears. So it's this thing where it seems like, as a whole, lots of people seem to misremember something, which feels uncanny.
Right,
Gotcha.
right. There's another one, like it was play it again, Sam. There is no again. He just says play it, Sam. I'm pretty sure.
Oh, cool. All right.
Yeah, I think,
I
or the inverse of that. But what people misremember that collectively and are certain about what their memory is, and it's just all wrong. So what is it we're misremembering about Mandela?
That he's not Dr. Martin Luther King.
What?
I think it might be
is
when he
everybody-
died is what people misremember.
All right. Well, there you have
Well,
it.
he's got the name. So the day we do discover parallel universes intersecting in ways that are interesting, Mandela is remembered for this. This is cool.
Very
I
good.
like that.
Yes.
And not Luke, not Star Wars,
Not the Luke effect.
Let there be some social justice
Right.
gained by the collision of two parallel universes. Well, Delilah, it's been delightful to have you on, and congratulations on your recently minted PhD. Good luck. Sometimes you need a little bit of that going forward in this universe. And if you make any new discoveries or you hear about anything very cool, give us a holler. We'll put you right back on.
Yeah.
Because it's
Tell
clear.
us first.
Will
Tell
do.
us first,
Will
Delilah.
do. Thank you so much for having me.
Don't let those Princeton people call the New York Times. You call Neil, get it on here first.
You got it.
Really good. This has been StarTalk Cosmic Queries Edition with Dr. Delilah Gates, a newly minted PhD at Princeton University, right down the block from us in New York. Chuck, always good to have you, man.
Always a pleasure.
Neil deGrasse Tyson here, as always, bidding you to keep looking up.